Hello there, and welcome to the Sleepy Space Channel. Directly above and below a black hole, along the single line it spins around, the universe builds two of the longest structures it knows how to make. Most pictures show a black hole as a featureless sphere, but that image quietly hides the truth. A spinning black hole has a real axis, and along it, from the two poles, twin beams of plasma are launched at nearly the speed of light. Held straight by wound magnetic field, they can reach for millions of light years, far larger than the galaxy that made them. Tonight we travel that axis slowly, from the still dark center out to the great soft clouds where the beams come to rest. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Let it all be far away and harmless. Settle in now and let yourself grow heavy. Let your shoulders soften. Let your breathing slow. Let the day fade gently away. Let's begin. A black hole is almost always drawn the same way. It is shown as a round, dark pit, pulling everything toward it evenly from every side, the same in all directions at once. Under that picture, asking what lies above it or below it seems to make no sense, because a perfect sphere has no top and no bottom. There is only inward, and inward, and inward again. And for a long time, that was close enough to how most people imagined these objects, as smooth drains in space with no sense of direction at all. The picture is incomplete, though, in one quiet but important way. Almost every black hole in the universe is turning, and a great many of them are turning at nearly the fastest rate that nature will permit. A spinning object is no longer the same in every direction. It has an axis, the single line it turns around, and that line gives it a real top and a real bottom. It is the difference between a still marble and a spinning top, and it changes the entire question we are asking. The spin is not an accident, and it is not rare. A black hole is born from collapse, and whatever it forms from is almost always turning already. A massive star rotates before it falls in on itself, and the cloud of gas that feeds a black hole afterward arrives with a sideways swing rather than a straight drop. All of that turning has to go somewhere, and it goes into the black hole itself. So the object that results is not a quiet sphere, but a spinning one, carrying the accumulated rotation of everything that ever built it. Once a black hole is allowed to spin, the words above and below stop being empty. The axis points somewhere. It marks two poles, one at the top and one at the bottom, and a plane that wraps around the middle at right angles to them, the way an equator wraps around a turning world. There is a geography here, after all. There is a direction that means around the side, and a different direction that means straight up and straight down, and the two directions turn out to hold completely different things. That difference is the entire subject of this video. Around the equator, in the plane of the spin, matter gathers. It collects into a flattened, glowing ring that circles the black hole many times before it falls, and that ring is the part almost every picture shows. It is the bright disk, the side view, the thing we usually mean when we picture a black hole at all. It is crowded and hot and loud with infalling gas. Directly above and below, out along the axis, through the two poles, the story reverses. The poles are not where matter piles in. They are where energy and matter are driven out. If the equator is the wide mouth of the black hole, the poles are closer to its exhaust, two openings aimed in exactly opposite directions, along which the system sends its power away into the night. And what comes out of them is the most far-reaching thing a black hole ever makes. So the question in the title has a real and specific answer, and it is stranger than the plain, nothing most people would guess. Directly above and below a spinning black hole lie two mostly cleared funnels, swept nearly empty of gas, threaded through with magnetic field that the spin has wound tight. And in a large share of active black holes, out of those two funnels climb two narrow beams of plasma, moving at almost the speed of light, reaching outward for distances that can be larger than an entire galaxy. They are called jets, and they are among the straightest, longest, most sustained structures anywhere in the universe. One climbs up from the North Pole. One descends from the South. They are near mirror images of each other, launched back to back along the one line the black hole turns around, and they can hold their aim for stretches of time longer than the age of the mountains on Earth. Nothing about them is gentle at the source, and yet from far enough away they resolve into something almost serene, two clean threads of light drawn out of a single point. Not every black hole is firing these beams at every moment. A black hole that has little left to feed on falls quiet, and its poles fall quiet with it, waiting. But the shape of the place is always the same, whether the engine is running or resting. There is a spin, and so there is an axis. There is an equatorial plane where matter would gather, and there are two polar directions where, given fuel, the power would leave. The architecture is built into the turning itself, and it is patient. The objects we are describing come in an enormous range of sizes, which only makes the shared shape more remarkable. The smallest black holes, left behind by collapsing stars, are only a few miles across, smaller than a city, and yet they can still raise these twin beams from their poles. The largest, sitting at the centers of galaxies, hold millions or billions of times the mass of the Sun, and their edges can be as wide as the orbit of a distant planet. Small or immense, the same simple rule holds. Where there is spin, there is an axis, and along that axis, there is an above and a below. To understand what sits in those two directions, then, we have to move slowly through the whole structure, from the middle outward. We begin at the still center, the black hole itself, and learn why it has an axis at all. We turn next to the bright equator, the disk of infalling matter, because the poles only make sense once the disk is clear. We rise up through the cleared funnels, watch the magnetic field win tight and let go, and follow the two beams outward, past the edge of the galaxy, all the way to the enormous soft clouds, where they finally come to rest. It is worth noticing how unusual it is to have a real up and down in space at all. Out among the stars, there is normally no true top or bottom. One direction is as good as another, and the words lose their meaning. A spinning black hole is one of the few places where nature draws a firm line and says, this way is the axis, and these two ends are its poles. In a universe with almost no preferred directions, the black hole quietly insists on one. That single line then organizes everything, which is why it repays such close attention. Choose any spinning black hole, anywhere, of any size, and its disk will lie in one plane, and its beams will leave along the one axis at right angles to that plane. The rule never varies. The matter gathers around the middle. The power leaves through the top and the bottom. Once you know to look for the axis, every one of these objects sorts itself into the same simple shape. Tonight we are not standing over a monster or peering down into a pit. We are studying an object, calmly and in order, the way one might study the workings of a great and silent machine. The black hole at the center will barely change through any of it. It simply turns, as it has turned for ages, and holds the whole arrangement in place around itself. Everything that follows hangs from that one quiet fact. A black hole spins, and so it has a line, And along that line, there is a direction we can honestly call up, and a direction we can honestly call down. Before we rise up to the poles, it helps to stand for a while at the center and be clear about what a black hole actually is. A black hole is a region of space where gravity has been concentrated so tightly that, past a certain boundary, nothing can move outward quickly enough to leave. Not a stone, not a spacecraft, not a beam of light. Inside that boundary, every possible path leads further in. Outside it, the ordinary rules still hold. That boundary has a name, the event horizon, and it is worth being careful about what it is and is not. The event horizon is not a wall, and it is not a surface made of anything. There is nothing there to touch. It is simply the line in space where the speed needed to escape rises to match the speed of light, and since nothing can go faster than light, nothing crosses back out. You could pass through it without feeling a single thing change, and yet from that moment on, every direction that seems like out would actually lead further in. The size of that boundary depends only on how much mass the black hole holds. A black hole, made from a single collapsed star, draws its horizon just a few miles across. A dark sphere you could fit inside a small city. A black hole, at the center of a large galaxy, grown over ages, can draw its horizon wider than the orbit of a distant planet, so large that light itself needs hours to cross from one side to the other. The same kind of object spans that entire range, from the size of a town to the size of a solar system. It is worth setting aside one very common idea, because it quietly gets in the way. A black hole is not a cosmic vacuum cleaner, roaming space and pulling things in. From any real distance, its gravity is no stronger than that of any other object holding the same mass. If the sun were somehow replaced by a black hole of exactly the same weight, the Earth would not be dragged inward. It would continue along its same orbit, in the same year, in a colder and darker sky. Only very close to the horizon does anything strange begin, and that closeness is the setting for everything else we will describe. Now we come to the feature that gives this whole video its shape, which is that a black hole spins. Almost all of them do, carrying the inherited rotation of the star or the gas that formed them, and many spin so fast that their outer edge is turning at a large fraction of the speed of light. Spin is one of only a few things a black hole can even have. Strip away every other detail, and a black hole is described by just its mass, its spin, and a faint electric charge that in practice is almost always negligible. Of those, the spin is what breaks the symmetry and hands the object an axis. A spinning black hole does something to the space around it that a still one does not. It drags that space into rotation. This is not the gas being pulled along, but the fabric of space itself being wound around the turning mass, the way thick honey is dragged into motion by a spoon turning at its center. Close to the black hole, this dragging becomes so strong that it can no longer be resisted at all. There is a region just outside the horizon where nothing can hold still, where every object and even every beam of light is swept around the axis, whether it wants to be or not. That region has a name, the ergosphere, and it matters more to our story than it might first appear. Within it, standing still is not an option that physics leaves open. Space is being turned so forcefully that to remain in one place, you would have to travel faster than light against the current, which cannot be done. Everything inside the ergosphere circles the black hole in the direction of its spin. And crucially, the ergosphere is not a sphere at all. It bulges out around the equator and pinches in toward the poles, so that even the shape of the dragged space knows where the axis is. This dragging of space is the reason the poles and the equator behave so differently, and it is worth sitting with for a moment. All of that wound-up motion is organized around a single line. The turning is fastest around the middle and calmest along the axis, and so the whole neighborhood of the black hole is sorted, quietly and completely, into an equator and a pair of poles. Long before any gas arrives, before any disk forms or any beam is launched, the black hole has already stamped its sense of direction onto the space around it. It is worth holding one more image steady before we move outward, because it runs against the mood of everything to come. The black hole itself does not thrash, or roar, or reach. It is, by any honest measure, the calmest object it is possible to imagine. It has no surface to churn, no flame to flicker, no weather. It is defined by almost nothing at all, a smooth and silent region carrying only its mass and its spin. Every violent thing we are about to follow happens outside it, in the matter and the fields that crowd around it. The center stays still, while the sky around it grows loud. Two more features of the horizon are worth knowing, because they sharpen the sense of it as a real place rather than an idea. The first is that time itself runs differently near a black hole. To a distant watcher, a clock lowered toward the horizon appears to tick more and more slowly, until, right at the edge, it seems almost to stop. An object falling in would appear, from far away, to slow and linger and fade at the boundary, rather than plunge cleanly through it. The nearer to the horizon, the slower the outside universe sees your time flow. The second is that the strength of a black hole's grip at the horizon depends on its size, in a way that runs against intuition. Around a small black hole, the pull changes so sharply over a short distance that anything approaching would be stretched thin. Around a giant one, the change is far gentler, and an object could cross the horizon smoothly, without being torn, feeling little unusual at the moment it passed. The largest black holes are, at their very edges, the mildest, which is part of why crossing one could be so strangely quiet. There is also a plainness to these objects, once they have formed, that is easy to overlook. Whatever fell in to make a black hole, whatever complicated star or cloud of gas, is erased as a detail. All that remains, all that the outside universe can ever know, is the mass, the spin, and a whisper of electric charge. Two black holes of the same mass and spin are identical, however different the things that built them. A black hole is among the simplest objects in all of nature, describable in just a few numbers, and yet it organizes the enormous structure we are touring around itself. A black hole is also not fixed in size, which matters for the long story of the poles. Every parcel of gas that crosses the horizon adds its mass to the black hole, and the horizon widens by a small amount in turn. Across the history of a galaxy, a central black hole can grow from a modest seed into a giant this way, swallowing gas and merging with other black holes, its boundary widening step by step. The same infall that feeds the beams at the poles slowly makes the black hole itself larger, so that feeding, growth, and launching are all one connected process. None of that growth changes the basic geometry though, and that is the reassuring part. A larger black hole simply draws a wider horizon and, if it spins, keeps its axis and its two poles like any other. Small or grown enormous, quiet or feeding hard, every one of these objects still sorts the space around it into an equator and a pair of poles. The size of the center changes across ages, the shape of the arrangement does not. So the setting is now in place. There is a dark, smooth boundary, the event horizon, small as a town or wide as a planet's orbit. There is a region just outside it where space itself is dragged endlessly around, faster at the equator, and gentler at the poles. And there is the axis, the one line the black hole turns around, already dividing the space around it into a direction along the side and a direction straight up and down. We have found our up and our down. Now we can begin to fill them in, and we start where the matter is, at the bright and crowded equator. To understand the poles, we have to understand the equator first, because the two are shaped by the same simple fact. Matter falling toward a black hole almost never falls straight in. It arrives carrying sideways motion, a swing left over from wherever it came from, and that sideways motion will not simply vanish. So instead of dropping to the center, the gas swings past it, loops around, and settles into orbit. Over time, countless streams of infalling matter flatten into a single turning sheet, circling the black hole in the plane of its spin. This is the accretion disk, and it is the bright, crowded structure that marks the equator. The disk forms in the equatorial plane for the same reason a ball of pizza dough spreads into a flat circle when it is spun. Anything orbiting at an angle is pulled and nudged until it joins the common plane, and the leftover motion of the whole crowd averages into one shared direction of rotation. What begins as a chaotic rain of gas from all sides becomes, given time, a smooth and organized wheel. And that wheel lies exactly at right angles to the axis, which means it lies exactly at right angles to the poles we are climbing toward. Within the disk, the gas is not simply coasting. Neighboring rings of the disk orbit at slightly different speeds, the inner ones faster, the outer ones slower, and where they brush against one another, they drag. Magnetic fields threaded through the gas become tangled and turbulent, and that turbulence acts like a kind of friction, passing motion outward from ring to ring. As a parcel of gas loses some of its sideways motion, it can no longer hold its orbit, and it drifts a little closer in. The disk is therefore always slowly draining inward, each parcel spiraling toward the center over many, many turns. That inward drift releases an enormous amount of energy, and this is where the disk begins to shine. Falling deeper into the black hole's gravity, the gas trades the energy of its height for heat, and the friction between the rings turns that energy into warmth and light. The process is remarkably efficient. Pound for pound, matter, spiraling through an accretion disk, can release far more energy than the nuclear fusion that powers the stars. A black hole that is feeding steadily can pour out more light than all the hundreds of billions of stars in its galaxy combined, from a central region no larger than our own solar system. The disk is not evenly warm across its width, and that gradient matters for what we see. The outer edges, far from the center, turn slowly and stay relatively cool, glowing in gentle infrared and visible light. But as the gas spirals inward, it moves faster and heats further until the innermost regions reach temperatures of millions of degrees. There, the disk blazes in ultraviolet and in X-rays, the hardest and most energetic light of the whole structure. So the disk shades from cool and dim at its rim to searing and brilliant at its throat, a single sheet running through an enormous range of temperature. There is a limit to how far inward the disk can smoothly reach, and it is one of the more elegant features of the whole arrangement. Close to a black hole, ordinary circular orbits stop being stable. There is an innermost stable circular orbit, a last safe ring, and inside of it no steady orbit is possible at all. Gas that drifts across that inner edge can no longer circle. It gives up, leaves the disk, and plunges the rest of the way to the horizon in a final quick fall. The disk, for all its brightness, has a clean inner rim, and inside that rim there is only the plunge. Where that last stable ring sits depends, once again, on the spin. A black hole that turns rapidly drags the space around it so strongly that matter can hold a stable orbit much closer in before it must fall. A black hole that barely turns forces its disk to end further out. So the spin does not only set the axis and the poles, it also reaches into the equator and decides how close the bright disk can crowd toward the center, and how hot and how brilliant its inner edge is allowed to become. The overall shape of the disk depends on how heavily the black hole is being fed, and the two extremes look quite different. Fed gently, with only a thin trickle of gas, the disk stays thin and flat, a shining record laid out around the center, barely puffed above its own plane. Fed heavily, with far more gas than it can quietly swallow, the inner disk bloats. It swells into a thick, puffed ring, closer to a donut than a sheet, with a rounded inner wall standing up above and below the plane. Even at its thickest, though, the disk still hugs the equator and still leaves the poles themselves comparatively open. That last point is the reason we have spent so long at the equator. However thin or thick the disk becomes, it is an equatorial structure. It lies around the middle. It thickens around the middle. It shines around the middle. And that means the two directions perpendicular to it, straight up and straight down along the axis, are left as the odd regions out, the places where the disk is not. The disk defines a plane, and by defining a plane, it defines the poles as everything the plane is not. From far away then, an actively feeding black hole would look like a brilliant flattened whirlpool of light, hottest and whitest at its center, cooling to a dull glow at its edges, turning slowly and pouring out radiation. It is one of the most luminous single objects the universe produces, and it is entirely a creature of the equator. And yet, for all that brightness, it is not the most far-reaching thing the black hole makes. The disk shines, but it stays close to home. To find the structures that cross a galaxy, we have to lift our gaze off the bright plane entirely and look straight up. The brightness of these disks is not a minor detail, because it is how we find black holes at all across enormous distances. A black hole itself gives off no light, but a black hole that is feeding lights up its disk so fiercely that the glow can be seen almost clear across the observable universe, a brilliant point marking a center too small and too dark to ever see directly. Much of what we know about distant black holes, we know from the light of the matter falling into them, and not from the black holes at all. The disk does not shine at a steady, unchanging level either. It flickers. Blobs and waves move through the turning gas, hot spots form and fade, and the total light rises and falls over time, sometimes across years, sometimes across only days. Watching a disk flicker is one way to sense how small the central engine really is, because only a compact source can brighten and dim so quickly. The flickering is the disk breathing as it drains inward, never perfectly smooth, always in motion. Not everything that leaves the disk goes down the poles either, and this is worth noting before we climb. From the broad face of the disk, a slower, wider wind of gas can be lifted off and blown gently outward, a soft breeze compared to the fierce polar beams. This disk wind spreads outward more or less in the plane, carrying away some of the infalling matter before it ever reaches the center. So the disk both feeds the black hole and sheds part of its load back into space, glowing all the while, losing as much as it swallows. The slowness of the inward drift is worth appreciating, because it stands against the fierceness of the light. A single parcel of gas may circle the black hole countless times, easing inward by the smallest steps, taking a long while to travel from the outer disk to the inner edge. The brilliance of the disk is not the brilliance of a quick fall, but of an enormous number of parcels, each giving up their energy gradually, all across the disk at once. The disk shines steadily because it is always draining, everywhere, gently. That steadiness is why a feeding black hole can hold its brightness for ages. As long as fresh gas keeps arriving at the outer disk to replace what has drained inward, the whole structure glows on, a long-burning light rather than a single flare. The equator, like the poles, runs on patience, a slow and continuous feeding that keeps both the disk shining and the beams flowing for spans of time that dwarf the whole of human history. So we leave the equator now, with its whirlpool of infalling fire, and we turn our attention to the two quiet directions the disk has left open. We rise off the plane, along the axis, toward the poles. And the first thing we find there is not the beams themselves, but the strange, cleared, superheated space that surrounds their base, the region that has to exist before any beam can be launched at all. Rising off the bright plane, the first thing we meet above the inner disk is not empty space, but a faint, superheated haze. Hovering just above and below the disk's hot center is a thin cloud of extremely energetic particles, far hotter even than the blazing inner disk beneath it. It is called the corona, borrowing the name from the thin, million-degree crown that surrounds the Sun. This corona wraps the innermost region of the black hole's disk, and it is responsible for much of the hardest, most energetic light the whole system gives off. The corona is thin, in the sense that its gas is spread out and sparse, and yet each particle within it carries a tremendous amount of energy. Light from the cooler disk below rises into this haze and is struck by the fast particles there, and each collision kicks the light up to higher and higher energy until it leaves as X-rays. So the region just above the poles of the inner disk acts like an amplifier, taking the disk's glow and sharpening it into something harder. Already, before we have traveled any real distance up the axis, the polar region is doing something the flat equator does not. Beyond that thin crown, though, the character of the polar direction changes completely, and this is the feature at the center of our question. The regions directly above and below the black hole, straight along the axis, are comparatively empty. While the equator is crowded with a dense glowing disk of infalling matter, the poles are swept clear, carved into two open funnels of thin gas, reaching up and down away from the center. If the disk is a packed and turning crowd, the poles are two quiet corridors leading out of it. The reason the poles are cleared follows naturally from everything we have already seen. Gas falling toward the black hole carries sideways motion, and that sideways motion steers it into the equatorial disk rather than down onto the axis. Very little material arrives moving straight along the poles, because straight-in paths are exactly the ones the spin does not favor. So the poles are starved of infalling gas from the start, simply because of the geometry of how things fall. At the same time, the poles are actively swept clean from within. The searing inner disk and its corona pour out radiation, and that radiation pushes on any gas that lingers along the axis, driving it outward. Magnetic forces, which we will come to shortly, add their own outward push. Between the lack of anything falling in along the poles and the steady pressure of everything being driven out along them, the polar funnels are kept open. They are the path of least resistance in the whole system, the two directions along which it is easiest to leave. This gives us the essential contrast of the entire topic, and it is worth stating plainly. At the equator, matter falls in. At the poles, matter and energy stream out. The very same object is an inlet around its middle and an outlet at its top and bottom. Gas spirals in along the crowded plane, gives up its light, and crosses the horizon. Energy climbs out along the two cleared funnels and leaves for the wider universe. One black hole, two opposite behaviors, sorted cleanly by direction. It is a little like the difference between the sides and the top of a chimney, though the comparison undersells the scale. Around the sides, everything is dense and turning and pressing inward. Straight up, there is a clear column, and along that column, the system vents its power. Except that here, there are two chimneys, not one, aimed in exactly opposite directions, so that whatever leaves the top has a twin leaving the bottom at the very same time. For now, before the beams are lit, we should picture the polar funnels simply as they are, as two open, cleared cones of thin plasma standing above and below the disk. They are threaded with magnetic field. They are lit faintly by the corona at their base and by the glow of the disk below. And they are waiting. They are the barrels of two enormous cannons pointed in opposite directions, kept clear and ready, needing only something to load and fire them. The funnels are the stage. What performs on that stage is magnetism, and to understand it, we have to look at what the spinning disk is doing to the magnetic field it carries. Even quiet, the funnels are strange places. They are among the few regions in the whole universe where the natural tendency of matter, which is to fall together and pile up, has been reversed, where the local rule is not inward, but outward. Stand in the plane of the disk, and everything drifts toward the center. Stand along the axis, and the current runs the other way, carrying things up and out. The poles are where a black hole, for all its inward pull, turns part of itself into a fountain. The walls of the funnels are, in part, the disk itself, and picturing that helps the shape make sense. When a black hole feeds heavily, and its inner disk puffs up into a thick ring, the rounded inner wall of that ring forms a pair of sloping funnels along the axis, like the inside of a curved horn opening upward and downward. Anything launched along the axis is guided by those walls, aimed and narrowed by the very shape of the swollen disk around it. The disk builds the barrel, as well as supplying the fuel. The contrast in density between the funnels and the disk is extreme, and it is what makes the poles usable as an exit. Down in the plane, the gas is thick and slow and pressing inward. Up the funnel, it is thin and open and easily driven out. A stream of energy trying to leave the black hole will always find the polar direction, the path of least resistance, simply because there is so little in the way. The poles are cleared, and being cleared, they invite everything that wants to escape. It is worth holding the strangeness of that inversion one more time before we light the engine. Everywhere else near the black hole, the rule is inward. Gas falls, matter gathers, the disk drains toward the center. Only along these two thin corridors does the current reverse and run outward. The poles are the two places where a black hole, for all its inward pull, keeps a door open the other way and stands ready to pour part of itself back out into the night. The poles are also the one clear path to the center, and that is worth a thought. Approach a black hole across its equator, and you would have to push through the crowded blazing disk to reach the horizon. Approach it straight down a pole, along the axis, and the way is comparatively open, a clear shaft of thin gas leading inward. The same funnels that let energy out are, in principle, the least obstructed way in, the two directions along which the center lies most nakedly exposed. There is a fitting contrast in that. The equator is where matter actually arrives, and yet it is the crowded, difficult route. The poles are nearly empty, and so they are the open route, though almost nothing ever travels down them. The busiest direction is the hardest to pass, and the emptiest direction is the clearest, and both facts follow from the same quiet sorting of matter into the disk and away from the axis. So, we have climbed off the equator and found the character of the poles. There is the thin, superheated corona, just above the inner disk, hardening the light into X-rays. There are the two cleared funnels stretching up and down, starved of infalling gas and swept by radiation and magnetism. And there is the quiet sense that these corridors are built to launch something, that they are shaped like the barrels of a machine that has not yet fired. To see them fire, we now follow the magnetic field down into the disk and watch what the spin does to it. The gas in the disk is not ordinary neutral air. It is plasma, a gas so hot that its atoms have been broken into free electrons and bare nuclei, and plasma has a special relationship with magnetism. Where plasma goes, magnetic field lines go with it, threaded through the gas as if frozen into it. The infalling matter that built the disk carried faint magnetic fields inward from far away, and now those fields are trapped in the turning disk, pinned into the plasma, forced to follow wherever the gas leads. As the disk turns, it carries those trapped field lines around with it, and this is where the spin begins to do its real work. A field line anchored in the inner disk or in the whirling space just outside the horizon is dragged around the axis again and again, once per orbit, endlessly. But the two ends of a field line do not turn at the same rate. The inner end, closer to the center, is swept around faster than the outer end. So the line cannot stay straight. It is wound up, twisted around the axis like thread being spun onto a spindle, tighter with every turn. Wind a magnetic field like that, and it stops lying flat in the disk and starts to climb. A twisted field line coils into a helix, a spring wrapped around the polar axis, rising up and down away from the disk toward the two poles. What began as a faint horizontal thread in the plane becomes a tightly wound tower of magnetic field standing along the axis. The spin has taken the field that the disk carried and stood it up on end, coiling it into two springs aimed straight along the directions we have been calling up and down. A wound spring holds energy, and it wants to release it, and a wound magnetic field is no different. The coiled field pushes outward along the axis and, at the same time, pinches inward around it, and those two tendencies together do something remarkable to the plasma caught in the funnels. The outward push flings charged particles up and out along the poles. The inward pinch squeezes them into a narrow column. The same wound field that launches the material also collimates it, gathering it into a tight, straight stream rather than letting it spray in all directions. There are two broad ways this magnetic launching is thought to happen, and they are not rivals so much as partners, often working together in the same system. In the first, the energy comes from the spinning disk. Field lines anchored in the orbiting plasma are flung outward, and gas beads its way up along them like water thrown off a spinning wheel, carried out along the poles by the turning of the disk itself. This is the gentler of the two engines, a magnetized wind lifted off the disk and funneled into the axis. In the second, the energy comes from the spin of the black hole itself, and this is the more remarkable idea. Magnetic field lines threading the whirling region just outside the horizon are dragged around by the rotation of the black hole, and that rotation feeds energy into them electromagnetically, like a dynamo turning motion into current and field. In this picture, the black hole's own spin is being tapped. Some of the rotational energy stored in the turning of space is drawn off along the magnetic lines and poured into the base of the poles, powering the beams from the center outward. That second idea deserves a moment of quiet wonder because of what it means. It means the most powerful sustained beams in the universe can be driven not by burning and not by any explosion, but simply by something turning. A black hole spins. A magnetic field is wound around it, and over ages the stored rotation leaks out along two thin lines into the dark. The engine at the poles runs on rotation and patience. It is closer to a flywheel slowly unwinding than to anything that flares or detonates. The launching itself happens in a compact region at the base of each pole, just above and below the inner disk and the horizon. There, in a zone not much larger than the black hole itself, the wound field grabs the plasma, flings it outward, and pinches it straight. Everything that will become a beam thousands or millions of light-years long is set in motion here, in a small, bright throat at the foot of each funnel. The poles are not just where the beams travel. They are where the beams are born. This also explains, at last, why the beams come in pairs, why there is always an above and a below rather than just one. The whole engine is organized around a single axis and a single sense of rotation. The field is wound the same way above the disk and below it, mirror reversed, so the launching happens at both poles at once, in opposite directions. One central spin, one magnetic geometry, and the result is two beams fired back to back. The symmetry of the jets is not a coincidence. It is written into the fact that a single spinning object cannot help but treat its two poles alike. The strength of the launched beams depends on how much magnetic field the black hole has managed to gather, and here the disk plays quartermaster. As gas spirals inward over ages, it carries field lines in with it and leaves them piled up near the center, so that magnetic field accumulates around the black hole like snow banking against a wall. Given enough time, the field near the poles can grow so strong that it pushes back against the very gas trying to fall in, holding the inflow at bay around the equator while standing ready at the poles. A black hole in that state is armed with about as much field as it can hold. It is worth being clear that spin alone is not enough to raise a beam. A spinning black hole with no magnetic field around it would turn quietly and launch nothing at all. It is the combination that matters, the spin to provide the energy and the field to carry it out. The magnetic lines are the wires along which the black hole's rotation is drawn off and delivered to the poles. Without the wires, the battery simply sits there, full and unused, and the sky above the poles stays dark. And the battery is enormous. The rotational energy stored in a fast-spinning giant black hole is greater than almost any other single store of energy in the universe, enough to power the brightest beams for ages and barely be lessened. The poles are where that reservoir is slowly tapped. Turn by turn, across ages, the black hole gives up a little of its spin to the field, and the field gives it to the beams, and the beams carry it away across the sky. The engine runs on the winding down of a top that was set turning long ago. The winding never quite finishes, and that is what keeps the engine running. As fast as the field is wound tight and flings its plasma outward, the turning of the disk and the black hole winds it again, so the coiled springs along the poles are continually being loaded and released. It is not a single throw, but a steady, endless cranking, a machine that stays powered as long as the disk keeps turning and the field keeps threading through it. The beams flow on because the winding goes on. This is why the launching is so steady rather than sharp. A single wound spring would fling its load once and fall slack. But a spring that is being wound as fast as it unwinds pours out a continuous stream, and that is closer to what the poles do, delivering their energy in a long, even flow. The engine at the base of each pole is less a cannon fired once than a fountain held open, quietly and continuously, by the turning at the center. So the funnels are no longer empty and waiting. The magnetic field carried in by the disk has been wound tight by the spin, stood up along the axis into two coiled towers, and set to flinging plasma outward from the base of each pole. The cannons are loaded and lit. What climbs out of them is the thing we came here to find, the two beams that reach further than anything else a black hole makes. It is time to follow them up and out, and to see just how narrow, how fast, and how far they run. Out of the base of each pole climbs a jet, and these two beams are the direct answer to our question. They are narrow streams of plasma, launched in opposite directions along the spin axis, one rising up and one descending down. In the most powerful black holes, they are among the straightest and most sustained structures found anywhere in nature, holding a single line across distances that dwarf the object that made them. When we ask what sits directly above and below a black hole, these beams are the fullest answer we can give. The material in the jets moves at nearly the speed of light. Flung outward by the wound magnetic field, the plasma is accelerated until its bulk motion is only a whisper below the fastest speed anything can travel. This is not the gentle drift of a breeze or the flow of a river. It is matter moving so close to light speed that the difference is measured in tiny fractions of a percent, sustained not for a moment, but along the entire enormous length of the beam. The jets are among the fastest large-scale flows the universe contains. What the jets are made of is worth pausing on, because it is so ordinary and so extreme at once. They are built from plasma, from electrons and bare atomic nuclei, and, in places, from the light cousins of matter, all braided together with magnetic field. It is the same basic stuff as the gas in the disk and the gas between the stars, only stripped bare, sped up, and organized. There is nothing exotic in the ingredients. The strangeness is entirely in the speed, the straightness, and the sheer sustained force behind them. The most remarkable feature of the jets may be how narrow they stay. A beam launched from a region smaller than a solar system can travel outward for thousands, even millions of times that distance, while barely spreading at all, holding a tight, pencil-thin line the entire way. This property is called collimation, and it does not happen on its own. Left to itself, hot plasma would billow outward and diffuse into nothing. The jet is kept narrow by the magnetic field wound around it, which pinches it inward, and by the pressure of the surrounding gas, which presses on it from the sides. Between the two, the beam is held straight over lengths that are difficult to hold in the mind. A jet is not a smooth, featureless ray, and the details along its length tell a story of their own. Here and there along the beam, brighter spots appear, glowing knots strung along the line like beads on a wire. These knots mark places where the flow is not perfectly even, where a faster pulse of plasma has caught up with slower plasma ahead of it and slammed into it, lighting up the collision. These are internal shocks, and they flicker and shift over time, so that a jet, watched patiently, is a living thing, brightening and fading along its length as new pulses race outward from the center. The jets also produce one of the stranger illusions in astronomy, and it is worth explaining gently because it sounds impossible at first. A jet, aimed close to our line of sight, can appear to move across the sky faster than light itself. Nothing is truly exceeding the light speed limit. The beam is simply chasing its own light toward us, so that the light it emits later has less distance to travel and arrives closer behind the light it emitted earlier. The result is that the motion looks compressed and sped up, a trick of geometry and light travel time. It is called apparent superluminal motion, and it is a sign that we are looking almost straight down the barrel of a beam pointed nearly at us. That same near light speed motion also concentrates and brightens the jet's light in the forward direction. A beam moving toward us has its glow gathered and intensified along its path, so that a jet pointed our way can appear far brighter than the same jet seen from the side. This is why orientation matters so much for how these objects appear, a point we will return to later. For now, it is enough to notice that a jet is not only fast and narrow, but also that its speed changes how bright it looks depending on where we happen to stand. Seen whole, then, a jet is a thread of ordered light escaping one of the most extreme places in the universe. It begins in a small, bright throat at the pole, is flung outward at nearly light speed, is squeezed straight by its own magnetic field, and carries brightening knots of shocked plasma along its length as it climbs. And there are always two of them, above and below, near mirror images running in opposite directions. The black hole sits at the center of this arrangement, still and silent, while two of the longest straight lines in nature are drawn outward from its poles. There is something quietly beautiful in how contained it all is. All of this speed, all of this power, stays gathered into two thin lines. The jets do not spray or scatter or fill the sky. They hold their aim. A black hole could, in principle, throw its energy off in every direction, but instead, it sends it out along just two, straight up and straight down, as neatly as a lighthouse sends its two beams. The most violent launching in nature is also one of the most disciplined. What exactly the jets are made of, at the finest level, is not fully settled, and that small uncertainty is part of their character. In some, the beam seems built mostly of ordinary matter, electrons and bare nuclei stripped from the disk. In others, it may carry a lighter mix, electrons paired with their mirror image counterparts, formed in the fierce fields near the black hole. Either way, the plasma is braided through with magnetic field, and it is that field, more than the matter, that gives the jet its shape and its discipline. The magnetic field in a jet is not tangled but combed, and this ordering is one of its quiet marks. Along much of the beam, the field lines run in an orderly way, wrapped and aligned, and that order reveals itself in how the jet's light is polarized, its waves leaning in a common direction. A jet is therefore not just a spray of fast particles, but a structured, magnetized thread, its field organizing the plasma along the whole enormous length of the beam. A jet often has an inner and an outer part, as well, like a fast core wrapped in a slower shell. The very center of the beam moves the fastest, close to the limit, while an outer sheath travels more slowly around it, buffering the quick spine from the gas outside. The two move together, the fast center of the jet drilling ahead, the slower sheath shielding it, so that the beam holds its form far longer than a single uniform stream ever could. For all their speed, the beams are also astonishingly thin, and that thinness is worth dwelling on. A jet can hold an opening angle so narrow that over a length greater than a galaxy, it barely widens at all, staying nearly as slender at its far end as near its start. To draw such a line by hand, you would need a ruler longer than a galaxy and a hand that never once wavered. The black hole draws it with its spin and holds it true across distances and times that have no easy comparison. It is a strange kind of restraint for so much power. The energy pouring from the poles could, in another arrangement, spray outward and light the sky in every direction. Instead, it stays gathered into two thin threads, disciplined by the magnetic field, aimed straight up and straight down. The most powerful sustained outflow in nature is also one of the most tightly held, spending itself along just two narrow lines rather than scattering into the dark. We have now met the beams up close, at the scale of their birth and their first climb. But we have not yet followed them to their end, and their end is very far away. A jet does not stop at the edge of the disk, or the edge of the black hole's neighborhood, or even the edge of the galaxy. To see where the answer to our question truly reaches, we have to pull back, and back, and back again, until the whole galaxy has shrunk to a bright dot, and the beams are still climbing outward past it into the dark. The jets begin in a region smaller than a solar system, in the bright throat at the base of each pole. That is worth holding on to as we watch them travel, because the contrast is part of the wonder. Everything that follows grows from a launching zone, no larger than the space around a single star, and yet it reaches outward to sizes that make whole galaxies look modest. The beams start small and do not stop. They do not stop at the edge of the disk. The disk, for all its brightness, is a local structure, hugging the center, and the jets pass beyond its outer rim while they are still gathering their speed. They do not stop at the edge of the black hole's neighborhood either, nor where the central bulge of stars gives way to the thinner outer galaxy. The beams simply keep climbing, straight along the axis, past every landmark the galaxy has to offer. From a small, stellar black hole, feeding on a companion star, the jets may reach outward for a few light years before they fade. That alone is a remarkable distance, longer than the gap between the Sun and its nearest neighbors, drawn out from an object only miles across. But these smaller beams are only the modest end of the range. The great jets, the ones raised by the giant black holes at the centers of galaxies, reach far, far further. From a supermassive black hole, the jets can extend for tens of thousands and hundreds of thousands of light years. And the largest known examples reach for millions of light years from end to end, stretching so far that the galaxy which launched them sits like a single bright seed at the very center of a structure vastly larger than itself. These are among the largest single structures the universe is known to contain, and they are built by an object at their center that would be invisibly small on any picture of the whole. Let that comparison settle for a moment, because it is the strangest fact in this whole subject. The influence that reaches directly above and below a black hole can be the largest thing the black hole ever makes. Not the disk, bright as it is. Not the galaxy full of stars around it. The jets and the structures they inflate can outmeasure all of it, reaching out of the galaxy entirely and crossing into the thin space between galaxies. The answer to what lies above and below is not a local answer. It spans distances usually reserved for the gaps between whole star systems and beyond. The jets are not only long, they are long-lived, and their patience is part of their reach. A single pair of beams can hold roughly the same orientation and keep flowing outward for spans of time far longer than the history of life on Earth. The engine at the poles does not fire once and fall silent. It runs and runs, feeding the beams for ages, so that the plasma launched long ago is still traveling outward, while fresh plasma is still being launched behind it. The line is continuous, from the center to a point millions of light years away. Because they hold their aim for so long, the jets trace nearly straight lines across those enormous distances. A beam that stays pointed the same way for ages, moving at nearly light speed, draws one of the straightest paths in all of nature, a line ruled across intergalactic space by the steady spin of a single black hole. There are few things in the universe as long and as straight at once. The jets are among them, quietly, without any fanfare, simply by keeping their direction. It is worth trying to picture the scale honestly, even though the mind slides off it. Imagine the galaxy that hosts the black hole shrunk to the size of a coin held at arm's length. On that scale, the jets would stretch out to either side far past the reach of your arms, past the width of the room, two thin lines running away from a coin-sized smudge of light in the middle. The thing at the center that made them would be smaller than a single grain of the coin's metal. Small center, immense reach. That reach is silent, too, which is easy to forget. For all the speed and power in the beams, there is no sound out there. and from far enough away, there is no sense of violence. There is only a long, thin line of faint light, drawn slowly across the dark, holding its shape over distances and times that have no comfortable comparison. The jets are ferocious at their base and serene at their ends, and most of their enormous length lies in that serene, far reach, gliding outward through nearly empty space. The space the great jets cross is the thinnest there is, and that thinness is why they reach so far. Between the galaxies, the gas fades to a mere handful of atoms in a volume the size of a small room, emptier than any vacuum that could ever be made on Earth. A beam driving through such emptiness meets almost nothing to slow it, and so it runs, and runs, gathering length across regions where there is scarcely anything at all. The very barrenness of intergalactic space is what lets the poles reach so far beyond the galaxy. The travel times involved are difficult to hold, and they lend their own kind of stillness to the picture. A beam reaching for 1,000,000 light-years is a beam whose far tip left the black hole 1,000,000 years ago and is only now arriving at its end. The jet is a single, continuous line whose two ends are separated not only by enormous distance, but by an enormous span of time. The near end young, the far end ancient, all of it drawn from one quiet center. Set against the galaxy that made them, the largest jets are almost beyond reason in their scale. A galaxy might measure 100,000 light-years across its bright starry disk. The largest jet pairs reach many times that, so that the entire galaxy, with all its hundreds of billions of stars, sits like a small bright seed at the midpoint of a structure far longer. The poles, in these cases, are the part of the black hole that most outsizes everything else around it. It helps to remember that the beams are still being fed the whole time they travel. The far end of a great jet is not a spent, abandoned tip, but the leading edge of a stream still connected, all the way back to the bright throat at the pole. Fresh plasma launched today will follow the same path the old plasma took, arriving at the far end ages from now, extending the line further still. A jet is less like an arrow already fired than like a hose held steadily open, its reach lengthening the longer it runs. That continuity is part of why the beams stay so straight. A structure fed continuously from a steady source along a steady axis has little reason to wander. It simply keeps laying down its line in the same direction, ages long, so that the finished jet records the unwavering aim of the black hole's spin across all that time. To look along a great jet is to look along a direction the black hole has held, without flinching since before our kind existed. So the honest answer to our question keeps growing the further we follow it. Directly above and below a black hole lie the cleared funnels, yes, and the two beams launched from the poles, yes. But those beams reach on, past the disk, past the galaxy, into the space between galaxies, for millions of light-years, held straight for ages by a single quiet spin. The reach is the real answer, and the reach is almost beyond measure. And even that is not the end of it, because eventually the beams meet something, and where they finally come to rest, they build structures, softer and even larger than the beams themselves. A jet cannot travel outward forever without meeting anything. Space between and around galaxies is thin, far thinner than the best vacuum ever made on Earth, but it is not perfectly empty. There is a faint haze of gas out there, and a beam traveling for hundreds of thousands of light-years eventually plows into enough of it to matter. Where the jet finally meets that resistance, its long, quiet journey ends in a bright and gentle collision, and something new begins to grow. At the far end of a powerful jet, where the beam rams into the surrounding gas, it forms a bright terminal shock. This is the point where the plasma, after its enormous straight run, is finally stopped and piled up, and where much of the energy it has carried all that way is at last released. These bright ends are called hotspots, and in the largest jets they mark the two furthest points of the whole structure, one high above the galaxy and one far below it, glowing where the beams come to rest. The hotspots are not the end of the story though, because the plasma that arrives cannot simply vanish. Having been stopped, it has nowhere to go but outward and back, spilling away from the point of impact and billowing into enormous rounded clouds. These are the lobes, two immense balloons of spent, magnetized plasma inflated above and below the galaxy, each one often far larger than the galaxy that feeds it. If the jets are the two thin beams, the lobes are the two soft clouds they blow at their ends. The lobes are among the largest coherent structures a single object ever creates. Fed steadily from the center by the beams, they swell outward for ages, growing into pairs of rounded shapes that hang above and below the galactic plane like two slow, glowing exhalations. They are quiet places compared to the fierce beams that feed them. The plasma in them has spread out and cooled from its first fury, and it drifts and glows faintly and slowly gives its energy back to the space around it. Around the beams themselves, on the way out, the returning plasma forms a sheath. Material that has reached the far hotspots and flowed back does not simply disappear into the lobes. Some of it wraps back along the jet, forming a cocoon of slower plasma that surrounds the fast central beam like the calm water around the core of a fast current. So a full jet, seen in cross-section, is a fast, bright thread wrapped in a slower, softer sheath, the two moving outward together, the beam drilling ahead and the cocoon trailing around it. Most of this enormous structure glows not in visible light, but in radio waves, which is why so much of it went unseen for so long. The fast particles in the lobes and beams, spiraling around magnetic field lines, give off a soft radio glow that our eyes cannot register, but our instruments can map. Seen in radio light, a galaxy that looks ordinary and quiet to the eye can reveal two giant lobes reaching far above and below it, a pair of soft radio clouds that dwarf the bright starlit disk at their center. Because the lobes last so long, they act as a kind of record, a fossil of what the poles have been doing. A beam can flicker or shift, and the central engine can quiet for a time, but the lobes remain, holding the shape of past activity long after the fact. Reading the lobes is like reading tree rings or old high water marks. The size and structure of the clouds above and below a galaxy tell the story of how its central black hole has been venting its energy through its poles across ages of time. The two lobes are, like the beams, near mirror images of each other. One reaches up, one reaches down, fed by the two opposite jets, inflated by the same central engine. Sometimes they are lopsided, because the gas on one side of the galaxy is denser than on the other and pushes back harder, so that one beam travels further before it is stopped. But the underlying pattern is symmetric. Two clouds above and below a shared center, the largest expression of the simple fact that a spinning black hole treats its two poles alike. There is a gentleness to the far structure that stands in real contrast to the beams. The jets are fierce, fast, and disciplined. The lobes they build are soft, slow, and enormous, drifting shapes of thin plasma that took ages to inflate and will take ages more to fade. It is as if the black hole's energy, launched as two hard straight lines, finally relaxes at the ends into two great quiet clouds, spreading and cooling in the dark, far from where it began. So the picture, directly above and below a powerful black hole, is now nearly complete, and it is larger than we might ever have guessed. At the center, the still black hole and its bright disk. Along the poles, the two fast beams. At the far ends, the two glowing hotspots where the beams stop, and around and beyond those, the two immense soft lobes hanging above and below the galaxy, mapped in radio light, holding the memory of the poles across time. From the center to the edges of the lobes, the whole thing is one connected structure, drawn along a single axis by a single quiet spin. Not all of these structures look the same at their ends, and the difference tells a quiet story about the beams that made them. Some jets stay tight and powerful all the way out, and end in bright hotspots at the very edges of their lobes, so that the whole structure shines most fiercely at its two far tips. Others are gentler and fray sooner, spreading into soft plumes that are brightest near the center and fade outward. The shape of the lobes reads back the strength and the steadiness of the poles that fed them. The lobes also carry a kind of clock inside them, written in the light they give off. The fast particles in a lobe slowly lose their energy over time, and as they do, the character of their radio glow shifts, the sharpest light fading first. By reading which colors of radio light remain, the age of a lobe can be estimated, how long ago the plasma within it left the beam. The oldest, faintest outer regions can hold plasma that streamed from the poles ages before the parts nearer the center. Sometimes the whole structure is bent, and the bending is a gentle sign of motion. When a galaxy drifts through the gas of a cluster, the thin resistance of that gas pushes the lobes backward, sweeping them into a pair of curved tails, trailing behind the galaxy's path, like long hair combed back in a slow current. Even bent this way, the two lobes stay matched and symmetric about the center, only swept to one side by the galaxy's patient passage through the surrounding gas. Standing back, the whole radio structure has a form worth picturing as one thing. At the center sits the small, bright core, the black hole, and its disk. From it run the two thin beams, faint and straight. At their far ends glow the two hotspots, and around and behind those swell the two great lobes, soft and rounded. Seen all at once in radio light, it resembles a slow, symmetric figure drawn across the sky, a bright point flanked by two long threads ending in two glowing clouds. The largest signature, a single object, writes upon the universe. And all of it is anchored to the axis. Move the black hole's spin, and the whole figure would swing to follow. The beams, the hotspots, the lobes, the cavities carved in the surrounding gas, every part of that enormous structure hangs from the one line the black hole turns around. It is a remarkable thing that a direction defined by a spinning object, smaller than a solar system, can organize a shape that reaches for millions of light years, and yet that is exactly what the poles do. And these clouds are not idle. In the places where galaxies gather together in great crowds, the lobes and bubbles blown from a central black hole do real work on everything around them. To see that, we turn from the shape of the structure to what it does, and we find that the poles of a black hole help decide the fate of far more than the black hole itself. Galaxies often gather in great crowds, held together by gravity into clusters of hundreds or thousands, and between those galaxies lies a thin, hot gas that fills the whole cluster. That gas is the reservoir from which new stars could one day form, if it were allowed to cool and settle and gather. Left alone, the densest gas at the center of a cluster would slowly radiate away its heat, sink inward, and condense into generation after generation of new stars. But very often it does not, and the reason has to do with the poles of the black hole at the cluster's center. The lobes and bubbles blown from a central black hole push out into that hot cluster gas and reheat it. As the beams inflate their clouds above and below the central galaxy, They carve out cavities in the surrounding gas, gently shouldering it aside and warming it as they go. That added warmth is enough to keep the gas from cooling and collapsing. The black hole, venting through its two poles, holds the whole cluster's reservoir at a low simmer, preventing it from ever quite settling into new stars. This is a remarkable reach for a single object, and it is worth stating slowly. Through its poles, a black hole no larger than a solar system can regulate the growth of an entire galaxy, and even an entire cluster of galaxies, deciding how many new stars are allowed to form across a span of millions of light years. The equator feeds the black hole. The poles feed that energy back out into the surroundings, and in doing so they govern the fate of far more than the black hole itself. Astronomers call this gentle governing feedback. The balance it strikes is surprisingly delicate. If the central black hole vents too much energy, it drives the gas away and starves itself, and the whole engine quiets down. As it quiets, the gas begins to cool again, sinks back toward the center, and eventually feeds the black hole once more, which relights the beams and reheats the gas. The system settles into a slow cycle of venting and cooling and venting again, a long, patient rhythm that keeps the cluster in a kind of steady state across ages of time. You can see the marks of this process written into the hot gas itself. In the thin glow of a cluster's central regions, mapped in X-ray light, there are often great rounded cavities, hollows scooped out of the hot gas, exactly where the black hole's lobes have pushed into it. These cavities sit above and below the central galaxy, matched to the beams that carved them, quiet evidence that the poles have been at work. The gas remembers where it was pushed and holds the shape of the pushing. There is something quietly profound in this arrangement, and it changes how we might think of the whole topic. We began by asking what lies directly above and below a black hole, expecting perhaps a simple answer about empty space or a beam of light. Instead, we find that the region above and below a black hole is where it reaches out and touches everything else, where it warms the gas of whole galaxy clusters and quietly decides how much of that gas will ever become stars. The poles are not only the most far-reaching part of a black hole. They are the part through which it shapes the wider universe. It means that the light of many galaxies, or the absence of new light in them, traces back in part to what happens along these two axes. A galaxy that has stopped forming new stars, grown old and red and quiet, may owe its stillness to the patient venting of the black hole at its center, breathing out through its poles just enough energy, just often enough, to keep the gas from ever gathering again. The stillness of an old galaxy can be the work of an axis we would never see by ordinary light. So the answer to our question has grown from the local to the enormous, and then from the enormous to something almost tender. Directly above and below a black hole are the funnels and the beams and the far hotspots and the great soft lobes. And through all of that structure, the black hole reaches out and keeps whole clusters of galaxies from cooling too fast, holding the pace of star formation across distances that beggar the imagination. The poles are how a black hole, silent and small, keeps its hand gently on the growth of the cosmos around it. For all its scale, this is a slow and steady process, not a violent one, and that steadiness suits the topic. There is no crisis here, no catastrophe. There is only a long, patient exchange. The gas cooling and feeding, the center warming and holding the gas, over and over, for ages. The poles of a black hole are the site of the most far-reaching influence it has, and that influence expresses itself not as destruction, but as a kind of tending, a keeping of balance across the crowded regions where galaxies live. There is a remarkable regularity that hints at how tightly the poles and the galaxy are bound together. Across a great many galaxies, the mass of the central black hole tracks the mass of the surrounding swarm of central stars, the two rising and falling together in near lockstep, even though the black hole is only a tiny fraction of the whole. It is as though the galaxy and its black hole have grown up together, each one's growth tied to the other, and the beams from the poles are one of the threads that binds them. The gentle warming we have described also settles a puzzle that once seemed stubborn. Left to itself, the hot gas at the center of a great cluster should cool and pour inward, forming enormous numbers of new stars, far more than are ever actually seen. The missing ingredient was the poles. The steady venting of the central black hole reheats the gas just enough to hold back that flood, which is why the centers of clusters are calmer and older than the simple picture predicted. The absent stars are absent because of an axis. This tending comes in more than one style, and both trace back to the poles. There is the quiet, steady manner we have followed, in which inflated bubbles warm the surrounding gas over ages. And there is a firmer manner, in which a fast wind and radiation from a heavily feeding black hole sweep the nearby gas outward more forcefully. In both, the black hole is regulating its own supply and its galaxy's growth at once, opening and closing the tap through the two directions of its axis. It changes the feeling of the word feedback to see it this way, as a kind of care rather than a force. The black hole is not attacking its surroundings. It is keeping a balance, warming the gas just enough, just often enough, to hold the whole system steady. Too little venting and the gas would collapse into a flood of stars. Too much and the black hole would starve itself. The poles thread the needle between the two, across ages, holding a great cluster of galaxies in a long and quiet equilibrium. There is a gentleness in that which is easy to miss beneath the scale of the numbers. The most far-reaching thing a black hole does is not to destroy, but to steady, to keep the gas of whole clusters from cooling too fast, to hold the pace of new stars even. Through its two poles, a silent central object tends the growth of everything around it, patiently, for longer than any star will ever shine. Having seen what the beams do, we can turn to a gentler and more human question. All of this structure is arranged around a single axis, which means the way it appears to us depends entirely on the angle from which we happen to see it. The same black hole can look like several completely different objects depending on whether we are looking at its side or straight down one of its poles. And that turns out to explain some of the brightest and most changeable beacons in the entire sky. Everything we have described is organized around one axis, and that single fact has a surprising consequence. The way one of these black hole engines appears to us depends almost entirely on the angle from which we happen to be looking. We do not get to choose that angle. Each black hole in the sky is tilted however it is tilted, and we see it from wherever we happen to sit, sometimes across its equator, sometimes at a slant, and sometimes very nearly straight down one of its poles. When we look at one of these systems from the side, across the plane of its disk, we see a relatively calm object. The disk stretches off to the sides. The two beams reach away to the left and right rather than toward us, and the whole structure appears, as it truly is, an engine seen in profile. From this angle we can trace the jets outward and map the lobes at their ends, because none of it is aimed our way. It is the view of an observer standing off to the side of the axis, watching the beams pass by. When we look almost straight down one of the poles, though, everything changes. Now we are staring into the oncoming beam, along the very line the plasma is traveling, and the jet is pointed nearly at us. Because that plasma is moving at almost the speed of light toward us, its light is gathered and concentrated and brightened in our direction, so that the object blazes far more brilliantly than it would from the side. A black hole whose pole happens to aim at Earth becomes one of the most luminous beacons in the entire sky. These pole-on objects also flicker and change with startling speed. Looking straight into the beam, we see the innermost, fastest, most changeable part of the jet, where knots brighten and fade as new pulses race outward. The brightness can shift over days, or even hours, a whole galaxy's worth of light, rising and falling on the timescale of a human season, all because we are looking down the narrow throat of a beam aimed our way. From the side, these changes would be lost in the calm. Head-on, they dominate everything. For a long time, the different angles fooled us into thinking we were seeing different kinds of objects. Seen from the side, one of these engines looked like a galaxy with two radio lobes. Seen at a slant, it looked like a brilliant point of light at a galaxy's center. Seen straight down the pole, it looked like a wildly flickering beacon of a third kind. Only gradually did it become clear that these might be one single family of objects, the very same kind of black hole engine, appearing in different guises depending only on how its axis happened to be turned toward us. That realization is a quietly beautiful piece of understanding. Much of the bewildering variety of bright galactic centers dissolves into one underlying picture seen from many directions. The object is always the same: a spinning black hole, a bright disk, two beams along the poles, two lobes at the ends. What changes is only our line of sight, only whether we are looking at the side of the axis or down the length of it. Orientation, not some real difference in the objects themselves, explains a great deal of the zoo. It is a gentle thing to rest on, that some of the brightest lights in the distant universe are simply black holes whose above happens to point our way. Out there, scattered across the far reaches, are countless of these engines, tilted at every possible angle. Most we see from the side, calm and mapped. A few are turned so that one pole aims almost exactly at Earth, and those few shine out across enormous distances, flickering, brilliant, pouring their beamed light straight down the line toward us across billions of years. When you look at one of those beacons, then you are, in a real sense, looking straight down the axis of a black hole into the mouth of one of its two beams. The light entering your instruments has traveled the entire length of a jet, from its bright throat at the pole to your eye, arriving concentrated and brightened by its own near-light-speed rush. The question of what lies directly above a black hole has, in these cases, a personal answer. What lies above it is a beam, and the beam is pointed at you. And this raises a natural curiosity. If we could somehow look directly down the axis of a nearer, quieter black hole, not blinded by a beam aimed our way, what would the region right around the poles actually look like? What is the face of a black hole, seen straight on, along the very line it spins around? That view has a character all its own, shaped by the strange way gravity bends light near the horizon, and it is worth pausing on before we shrink the whole picture down to the small black holes scattered through our own galaxy. Seen face on, along its axis, a black hole does not appear as a simple black dot. The gravity near it is so strong that it bends the paths of nearby light into curves, gathering the glow of the surrounding disk and wrapping it around the dark center. What we see is a bright ring of light encircling a round shadow, the shadow marking the region from which no light escapes, the ring marking the glow of hot gas bent around it. Looking down the axis, the black hole shows us a dark eye ringed in fire. That ring is partly an illusion of bent light, and understanding it is one of the quiet pleasures of the subject. Some of the light in the ring comes from gas on the far side of the black hole, behind it, whose glow has been curved up and over the top and brought around to our view. Gravity lifts the hidden far side of the disk into sight and lays it around the shadow like a halo. So the face of a black hole shows us things that should be hidden. The back of the disk folded forward, the underside brought up, all wrapped around the dark center by the bending of light. Closer in than even that ring lies a sharper, fainter circle, where light itself can travel in a nearly closed loop around the black hole before escaping. This is the region where a beam of light can orbit, circling once or many times, held in a tight ring just outside the point of no return. It traces the thinnest, cleanest circle in the whole scene, the last ring of light that can still get away. And it marks, as nearly as anything can, the true edge of the shadow. Along the axis, straight above and below, this ring of orbiting light is part of what waits. So the face on view, the view straight down the pole, is its own strange world. There is the round shadow of the horizon, the bright bent ring of the disk's light wrapped around it, and the fine circle of light that has orbited the black hole before slipping free. It is the calmest and most symmetric way to see one of these objects, a still dark eye ringed in light, quite different from the fierce beamed beacons and quite different from the profile view of jets and lobes. And it exists at both poles at once, above and below, two dark eyes looking out along the axis in opposite directions. It is worth saying plainly that these rings are not only theory. Patient work, joining instruments spread across the whole width of the Earth into a single enormous eye, has actually captured the shadow and its bright ring around a giant black hole, turning a prediction into a picture. What had once been drawn on paper as a dark circle wrapped in light was seen, at last, as a real ring of glow around a real round shadow, looking much as the bending of light had promised it would. Seeing it confirmed something quiet about the axis as well. The ring is very nearly circular, which tells us we are looking at the object close to, along its pole, rather than across its equator. A black hole seen edge-on would show a more lopsided, flattened shape, its near side brightened and its far side dimmed. A near circular ring is the face of a black hole met close to head-on, its axis turned toward us, its two poles very nearly in line with our view. There is a quiet lesson in how much the angle matters, and it softens the whole idea of these objects. The fierce, flickering beacon and the calm, mapped galaxy and the still dark ring are not three different beasts to be sorted and feared. They are one gentle fact seen three ways, one spinning black hole with one disk and two beams, turned at three different angles to our line of sight. What might have looked like a crowd of strange and separate things becomes a single, understandable shape, only rotated. And rotation is all it is. Nothing about the object needs to change from one appearance to the next, only our accidental place relative to its axis. Somewhere out there, a beacon that blazes for one distant observer looks like a quiet lobed galaxy to another, off to the side, simply because the two of them lie at different angles to the same set of poles. The variety is in the viewing, not in the thing being viewed. Having looked the giant black holes in the face, we can shrink the scale now and find that this same architecture, disk and poles and beams, repeats in miniature much closer to home among the small black holes that are scattered by the many through our own galaxy. The giant black holes at the centers of galaxies are not the only ones that raise beams from their poles. Scattered through every galaxy, including our own, are far smaller black holes, the collapsed remains of massive stars, only miles across. Most of them drift alone and unfed, dark and silent. But some of them travel in pairs, with an ordinary star, circling close together, and when a small black hole is bound to a companion, it can pull gas from that star and build, in miniature, the very same structure we have been describing. When a stellar black hole draws gas off its companion, that gas cannot fall straight in any more than it could into a giant. It carries sideways motion, swings into orbit, and settles into a small, hot accretion disk around the black hole, glowing fiercely in X-rays. And above and below that little disk, along the small black hole's spin axis, the same magnetic machinery can take hold, launching two small beams from the poles. The whole architecture repeats at a fraction of the size, an engine built to the same plan but scaled down to the remains of a single star. These scaled-down systems have a wonderful advantage for anyone trying to understand the poles. Because they are so much smaller, everything about them changes far faster. A giant black hole's beams evolve over ages, far too slowly to watch. But a stellar black hole can brighten, launch blobs of plasma from its poles, and quiet again over mere days and weeks. We can watch a full cycle of the engine play out, a disk flaring up, the poles firing, the beams fading, in the span of a single season, like seeing in a small model what the giants do across eternities. Some of these small systems put on a particularly clear show, flinging distinct blobs of plasma from their poles during outbursts, blobs that then race outward along the axis, and can even appear to move faster than light, in the same illusion of perspective we met before. Because they mimic their giant cousins so closely, in miniature and at speed, these systems have earned a fitting nickname that casts them as small-scale versions of the brilliant beamed beacons in distant galaxies. They are the local, fast-running models of the same grand machine. What these small engines prove is important, and it is quietly reassuring. The above and below structure of a black hole is not some special property reserved for the monsters at the centers of galaxies. It is a general feature of how any spinning black hole interacts with matter that falls toward it. Give a black hole of almost any size a disk to feed on and a magnetic field to wind, and it will tend to raise beams from its poles. The pattern is the same from the smallest to the largest, written into the physics rather than into the scale. It means that even now, somewhere in our own galaxy, small black holes are quietly running this same engine, drawing gas from companion stars, spinning up their little disks, and firing thin beams from their poles into the surrounding dark. They are scattered through the same starry expanse we live in, unseen by the eye, each one a tiny image of the enormous structures we have been touring, each one with its own above and its own below, its own two directions where energy leaves along the axis. The way these small systems feed is worth picturing, because it is so much more immediate than the slow drip of a giant. A stellar black hole and its companion star can circle so closely that the black hole's gravity peels a stream of gas off the star's surface, a bright ribbon spiraling across the gap and coiling into the little disk. Sometimes the flow is steady, and sometimes it comes in sudden outbursts, when gas that has piled up in the disk finally slips inward altogether and the whole system flares. During these outbursts, the little engine cycles through distinct moods, and the poles switch on and off as it does. In some states, the disk reaches close to the black hole, and a steady beam flows from the poles. In others, the inner disk pulls back, the mood shifts, and the beam sputters or shuts off entirely, sometimes flinging out a last bright blob of plasma as it goes. Because all of this plays out across weeks, we can watch the poles light and darken in something close to real time, a thing no giant will ever let us see. The way we notice these systems at all is through that flaring. A small black hole feeding quietly is easy to miss, but when it flares, its X-rays brighten across the sky, and radio instruments can catch the blobs of plasma streaming from its poles and even track them moving outward night after night. From those moving blobs, we can measure the speed of the beams and watch the same apparent faster-than-light motion that the giants show, played out small and quick and near at hand. What all of this makes plain is the constancy of the pattern. Whether the black hole is the mass of a single star or of a billion suns, whether its beams change over weeks or over ages, the arrangement is the same. There is a disk at the equator, and there are beams at the poles. The scale changes, the speed of the show changes, but the architecture does not. The above and below of a black hole is one of the most faithful shapes in all of nature. These nearby systems also let us test the grandest idea of all, that the beams draw their power from the black hole's spin. Because we can watch a small black hole change from week to week, we can look for the moments when its beam is strongest and ask what the disk and the spin are doing at that time. The little engines become a proving ground, close enough and quick enough to study, for the same physics that lights the giant beacons at the far edge of the universe. There is something companionable in knowing they are near. The distant beamed beacons are billions of light years away, seen as they were long ago. But these small engines are here, in our own galaxy, running tonight, flaring and quieting on a human timescale. When one of them lights its poles, it is doing so now, close by, a small living example of the same shape we find at every scale, drawn quietly in our own starry surroundings. And this brings the whole subject close to home, closer than the distant beamed beacons or the giant lobes of far-off clusters. The architecture of the poles is not only out there, at cosmic distances, in objects billions of light years away. It is here, in our galaxy, at every scale. Which naturally turns our attention to the largest black hole in our own neighborhood, the giant one that sits at the very center of the Milky Way, and to the question of what lies directly above and below it. At the center of our own galaxy sits a supermassive black hole, millions of times the mass of the Sun, and by the standards of everything we have described tonight, it is remarkably quiet. It is feeding only slowly, on a thin trickle of gas, and it is not launching great beams from its poles right now. If it has any jet at all at present, it is faint and modest. The giant at the center of the Milky Way is, for the moment, a sleeping engine, its poles nearly still. That quiet is worth appreciating, because it is not the same as emptiness. The black hole is there, turning, with its axis and its two poles, like any other, holding the same architecture we have followed all night. It simply lacks, for now, enough falling matter to light the machine to full power. Its disk is thin, its corona faint, its funnels open but idle. Above and below it, at this moment in cosmic history, there is mostly the quiet of a fire, banked low, waiting for fuel. But there is a clue written across the sky above and below the center, and it changes the story. Reaching far out of the plane of our galaxy, above and below the central regions, are two enormous rounded clouds of hot, energetic gas. They stand out from the center of the Milky Way like a pair of great balloons, one rising far above the galactic plane and one descending far below it, matched and opposite, centered on the core. They are among the largest structures in our galaxy, and they hang exactly along the axis where a black hole's poles would point. These great bubbles look very much like a fossil, the leftover mark of a time when the center was far more active than it is tonight. They appear to be the cooling remains of a past outburst, a period when the black hole at the core fed heavily and vented its energy through its poles, blowing these two clouds above and below the plane before falling quiet again. What we see now is the slow aftermath, two soft mountains of hot gas still standing above and below the galaxy, holding the shape of an eruption long past. So the question that titles this video has an answer written into our own sky. if we know how to look for it. What lies directly above and below the black hole at the center of the Milky Way? Two great bubbles of hot gas, quiet now, marking an axis that was once fierce and may be fierce again. The poles of our own central black hole have not always been still. They have breathed out structures larger than almost anything else the center of our galaxy has ever made. And the evidence still hangs there, above and below us, faint and enormous. There is a gentle symmetry between this and something an earlier journey explored, when we looked at what lies straight up and down out of the plane of the Milky Way as a whole. Then we found that the vertical direction, out of the galactic disk, holds far more than empty space, that above and below the bright band of stars there are halos and streams and quiet structure reaching into the dark. Here we find the same lesson concentrated at the very center, where a single black hole has stamped its own above and below onto the galaxy in the form of two great glowing clouds. It also draws a soft thread back to an earlier tour through the quiet world of black holes themselves, when we considered these objects as a whole, their horizons and their strange interiors and their slow grip on the matter around them. Tonight we have narrowed all of that down to a single direction, straight up and straight down, and found that the axis is where a black hole does its loudest and most far-reaching work. The same objects, seen along their one line, reveal a face they never show from any other angle. That our own galaxy carries this mark is a quiet kind of comfort. We are not living beside some dead and featureless pit at the center of the Milky Way. We are living in a galaxy whose central black hole has an axis and a history, and two great soft bubbles above and below the plane to show for it, cooling slowly across ages. The center is quiet tonight, but the sky remembers a time when it was not, and holds that memory in the shape of the poles. The scale of these two bubbles is hard to overstate, even set against the whole galaxy. Each one reaches many thousands of light years out from the plane, together spanning a large share of the width of the galaxy itself, standing above and below the center like a pair of enormous soft wings. They glow most clearly in the high-energy light our eyes cannot register, in gamma rays and X-rays, which is part of why they went unnoticed for so long despite their size. They were there, all along, above and below us, waiting to be seen in the right kind of light. Their quiet suggests an age. The outburst that most likely blew them appears to have happened long ago, on the order of a few million years, which is recent by the clock of a galaxy, but far older than our own kind. Since then, the center has mostly rested, feeding lightly, flaring now and then, but never with the old force. The bubbles are the slowly cooling breath of that older, fiercer time, still hanging in the sky, not yet dispersed. There is a patience in that image worth resting on. The giant at our galaxy's center is not gone and not dead. It is a sleeping engine beside a pair of monuments to the last time it truly woke. Its poles are quiet tonight, but they have not always been, and the two great bubbles are the proof, holding the shape of an ancient outward breath above and below the plane where we live. It is worth pausing on how ordinary our galaxy is in this, because that ordinariness is its own comfort. Nearly every large galaxy is thought to hold a giant black hole at its center, each with its own axis, its own quiet or active poles, its own history of venting into the space above and below its plane. Our galaxy is not special in having such an engine at its core. It is one of countless galaxies, each turning around a small, dark center, each marked in its own way by the two directions of an axis. So the bubbles above and below the center of the Milky Way are not an oddity, but an example, one nearby instance of a pattern written across the whole universe. Look out at the galaxies scattered through the dark, and a great many of them carry, seen or unseen, the same mark, the same pair of structures reaching above and below a central engine. What hangs over our own galaxy's center is a local copy of one of the most common arrangements in the cosmos. And so the architecture we have followed from the disk to the distant lobes turns out to run straight through our own home. There is an above and a below at the center of the Milky Way, marked by two enormous clouds. There are small black holes scattered through the same starry expanse, each with its own quiet axis. The pattern is everywhere, at every scale, near and far. It only remains for Z to draw the whole picture together and to rest for a while in the quiet symmetry of a thing that sends its power out along just two opposite lines. We have traveled the whole length of the answer now, from the still center out to the far soft lobes, and it is worth gathering it into one quiet picture before we let it rest. At the middle sits the black hole, smooth and silent, turning as it has turned for ages. Around its equator lies the bright disk of infalling matter, hottest at its throat, pouring out light. And along its two poles, above and below, run the cleared funnels, the wound magnetic field, the two fast beams, the far hotspots, and the two great glowing clouds. One connected structure, drawn along a single line by a single spin. The deepest feature of that structure is its symmetry, and it is a restful thing to hold in mind. Whatever streams up from the North Pole has a near twin streaming down from the south. The two beams mirror each other. The two lobes mirror each other. The two dark faces along the axis look out in opposite directions, matched and balanced. A spinning black hole cannot help but treat its two poles alike, and so the most extreme engine in the universe is also one of the most symmetric, balanced above and below around a still center. The axis is also remarkably steady, and its steadiness is part of its calm. Held in place by the black hole's spin, the poles keep their aim across spans of time longer than mountains last, so the beams trace nearly straight lines outward, patient and unwavering. There is no thrashing here, no wild swinging of the beams across the sky. There is only a long-held direction, a single line kept true for ages, along which the black hole quietly sends its power away into the dark. From close up, the poles are the site of the most violent launching in nature, and there is no need to pretend otherwise. Plasma is flung outward at nearly the speed of light. Magnetic fields are wound to the snapping point and let go. Beams drill across whole galaxies and slam into the gas beyond. But from far enough away, all of that resolves into something calm and orderly, a still dark center, a flat bright disk, two clean threads of light, and two soft clouds glowing faintly above and below. The violence is real, and so is the stillness. They are the same object, seen at two different distances. That may be the quiet gift of this whole subject, that the largest and fiercest things a black hole makes are also the most balanced and the most patient. The center never rages. It only turns. The energy leaves along just two opposite lines, as disciplined as the two beams of a lighthouse, and comes to rest at last in two great clouds that spread and cool and fade across ages. Even the most powerful engine in the universe, seen whole, is mostly stillness, with two thin lines of light drawn out of a single quiet point. There is a comfort in scale here that is worth naming before we close. The black hole is small and silent at the center, and yet around it hang structures that reach across and beyond a whole galaxy, all of them balanced, all of them slow. Nothing in this picture is in a hurry. The beams have flowed for ages. The lobes have taken ages to inflate and will take ages more to fade. Set beside such patience, the worries of a single night grow very small, and that smallness is its own kind of rest. There is comfort, too, in how little the center asks. The black hole does not reach for us or need us to watch. It simply turns and lets its light leave along two quiet lines and keeps its balance whether anyone is looking or not. It has done so since long before there was anyone to wonder about it, and it will go on doing so long after this night is forgotten, indifferent, and steady, and calm. So when you picture a black hole now, you can let go of the plain dark pit that pulls evenly from every side. In its place, you can hold something with a real shape and a real direction. There is a middle where matter falls in and shines. And there is an above and a below, along the one line it spins around, where the sky does something it does nowhere else, sending two beams of light climbing outward into a distance no night is long enough to cross. Before we let it go, it is worth gathering the whole journey into a single slow breath. We began at the smooth, silent center and learned that it spins and so has an axis. We watched matter gather at the equator into a bright, draining disk, and we rose off that plane into the cleared funnels of the poles. We saw the magnetic field wound tight and the two beams launched, followed them past the galaxy into the space beyond, and watched them come to rest in two great soft clouds. And we found the same shape everywhere, in small black holes nearby, and in the quiet bubbles above and below our own galaxy's center. All of it, from the disk to the furthest lobe, hangs from one quiet line. The black hole turns, and its turning sets the axis, and along that axis, the answer to our question unfolds, from the corona at the base of the poles out to structures larger than galaxies. There is nothing frantic in any of it when it is seen whole. There is only a slow, balanced arrangement, held steady for ages around a still and silent center. And so we leave the black hole turning slowly in the dark, its two thin beams of light climbing away above and below, patient and unhurried, into that distance beyond crossing. The center stays still. The axis holds its aim. The two great clouds hang quietly above and below the galaxy, cooling by the smallest degree across ages that make a human life look like a single breath. There is nothing here to fear, and nothing here that needs you to watch it. It has kept its balance for a very long time, and it will keep it long after this night is over. Let your breathing slow now, and let it fall into its own easy rhythm, in and out, like something turning gently on a steady axis. Let your shoulders soften. Let the day you carried settle and drift away from you, out along a quiet line, the way a black hole sends its light out into the dark and asks nothing back. Let your thoughts grow slow and far and dim until they are only faint glowing clouds, somewhere above and below, cooling towards stillness. The center of you can stay quiet and turning, while everything else drifts outward and fades. Sleep well, and good night.